Hey everyone, Corey and Victoria here. We are the Professors Du Bois, and in this lecture we're going to talk about solution and ion concentrations in molarity?
Molarity, what is that? All right, so we've been talking about reactions, right? So we've been learning about reactions, and we know how to identify what types of reactions they are, how to predict the products if we're only given the reactants, balance those equations, and we've used those equations and those reactions to calculate things. So we calculate maybe how much product can we make, but how do we use solutions in calculations and in reactions? I mean, how do we solve and answer a question like how much sodium hypochlorite, which is your chlorine, how much do I add to my swimming pool that happens to be 5,000 gallons? Or how much magnesium and hydrochloric acid do I need to generate a liter of hydrogen gas if I'm using hydrochloric acid as a solution?
Well, I think I got this, because if we have a balanced equation, I can just weigh the solution, and then I can use the mass of the solution and get to moles. How would I do that? That's the problem with the solution is we don't know how many moles are in that solution if we just weigh it. It could imagine a saltwater solution. There could be a little bit of salt in there or a lot of salt, and if we weighed that amount, we just wouldn't know from the mass. We can measure the volume, so the volume is going to be kind of our ticket to get us started, and we're going to use a new unit called molarity, and this is a concentration. It's in moles of solute divided by liters of solution. You'll see this written as a big M, and it's the same thing as moles over liter, and I like to write it as moles over liter just because it jumps out at me as a factor. That's right. So these moles could be atoms, molecules, or ions. We're going to do some ions soon.
So you will invariably need to calculate molarity for different solutions. So here's an example where we want to find the molarity, and we have the volume in milliliters, and we have the moles provided. So since molarity is moles per liter, we have to convert our milliliters to liters first, and then we can do the simple division down here and get a molarity.
So another example, we've got an amount in moles of sodium chloride, and we have a solution with a volume in liters. So we can just take the moles, divide by the liters, and we've got our molarity. We can write that as moles per liter. That's the way I like it. We can write it as big M, capital M. That's molarity. And another thing you'll see sometimes are these like square brackets around the solute, and what that means is it says the concentration of this NaCl in this case. That's those brackets means this is the concentration of. So in this case, that was a concentration in molarity.
Yep. So we can then use this molarity of a salt to determine the molarity of the ions that it creates in solution. And this is like one more step that you have to take, because you need to write the dissolution reaction for your salt so that you know what your mole-mole ratio is of your ions to your salt, so that you can get the molarity of the ions, because the molarity of the ions may or may not be the same as the salt that it went in to dissolve it.
Yeah, I see a 2-to-1 ratio there.
Right. So here's an example. We've got a molarity of our calcium chloride here, and we write our balanced equation. We notice that we have 2 chloride ions for every 1 calcium chloride. So if we have our molarity of calcium chloride, now we usually say start with what you know that's not a factor. In this case, we're starting with a factor, but we're only going to cancel part of it. So that's why we want to write the capital M as moles per liter. And moles of what? Moles of calcium chloride per liter. We're going to cancel moles of calcium chloride and change that to moles of chloride ion from our balanced equation. So you might have been able to do that in your head, but it's really nice to be able to cancel the units so that you can see this is the moles of chloride ion per liter, and then you don't mess it up by dividing when you should have multiplied or whatever. If you cancel your units, you can't go wrong.
That's kind of like the first time we've seen a unit that didn't get canceled out early on. You know, that liter there. Right. That liter's still there. So we have moles of Cl minus, and we're still in 1 liter, and we can write that as a capital M. Now this question's a little more difficult because we've got this salt and they give us the mass. So we have to figure out, we're going to have to figure out the molarity based on the mass. They didn't just give it to us. So we've got the 15 grams. Well, we can use the molar mass to get the moles. And then we have the volume given to us. It's a 500 ml flask. So we're going to calculate the molarity of that salt first, starting with the mass. And we need moles and liters. So there's going to be kind of a two-step calculation there.
For sure. So we have our mass of our salt, and this is just the molar mass from the periodic table for that entire salt. And this gives us some moles of, so we turn grams into moles of our salt. And if we bring this down and divide by the total liters, that was in the problem, said that we had 500 milliliter flask, so that's 0.5 liters. That gives us our molarity of our salt. Now, if we use our balanced equation to cancel moles of salt and turn it into moles of our ion, in this case, when sodium sulfate broke apart, it broke apart into 2 sodium ions. Then there's our 2-to-1 ratio, so we have twice the concentration of our sodium ion as we did our salt.
I'd like to point out one thing there. I noticed that when you calculated the moles of the sodium sulfate, you reported a 3 sig figs. And the reason you did that is you weren't done with the calculation. So we don't want to be rounding early. If there's more calculation to do with that number, keep at least one extra decimal or one extra significant figure in there or more. I often just use all of them in my calculator until I get to the very end and I'm ready to report the value, and then I round to the correct number of sig figs.
Right. And I would recommend even pausing the video right now and try this. Try this by rounding this to the correct number of significant figures if we were going to be done. So it was 2. If you round this to 2, 0.11 you'd get, right? 0.11 moles. If you put that in down here, you'll notice that your answer changes. So give that a try.
Sometimes those little rounding errors can have a big effect too. I mean, they don't always, but we want to be careful. Here's your practice. So we have got an iron 3 nitrate in a 250 ml flask. So we want to determine the nitrate ion concentration. You're going to have to write a dissolution reaction showing this iron nitrate going completely into its ions. Make sure you're balanced, and then you'll have to calculate the molarity of the salt and use that balanced equation.
Yep. Pause the video. All right, here's your answers, and we've showed you 2 different ways to tackle this problem. And the first one is to take your mass of your salt and turn it into moles of ion. Just write to moles. So molar mass, 3-to-1 ratio, and we haven't calculated molarity yet. So this is just grams to moles, moles to moles. Then you can divide by the total volume and get your molarity. Or you can do it the way we've been showing you, which is calculate your molarity of your salt, then use your mole-mole ratio to your ions to get your ion molarity. Either way.
You've got options.
You've got options. And that concludes this molarity and ion concentration lecture, and we hope you enjoyed it, and come back and see us again soon.
Thanks for watching.